right, so on to the main part of this chapter, the conservation of momentum. So the first thing we're going to do is start with why is momentum conserved? What are the conditions for that? And then we're going to look at the different types of conservation of momentum and some examples. So sit back and learn something, I guess. So conservation of momentum is based on the third law. Whenever any two things interact with some sort of force, whether it's gravity, applied forces, any forces whatsoever, the forces between them are going to be opposite and equal. And when those two objects interact, they're going to interact for equal amounts of time. So if I push on my one hand, it's going to push back for an equal amount of time that I'm pushing on it. This means that if I have force times delta time, they're going to have equal and opposite changes in momentum. And so we're going to change that delta to final minus initial. Now, a new thing we do this chapter is we use a prime symbol to denote after this interaction. For those of you in calculus, I know that might be a little confusing because you use it for derivatives, but here we're using it for after that process. So we're using it in a similar way. And so the final momentum after the collision minus the initial momentum is equal to the final minus the initial on the other side. We do have on this left side, though, some negative signs. So what happens is this ends up being negative, this ends up being positive because we have that negative sign out front. Now what I can do is I can move all of my initials to one side, my finals to the other side, and I end up with my two initials added together, my two finals added together, which means the momentum before is equal to the momentum afterwards. Conservation of momentum. Now we typically write this in this form where we talk about the mass times the velocity plus the mass times velocity. Now do remember that these are vectors. I didn't draw them on there, I guess, but they are vectors, meaning there is an arrow on every single one, so we need to maintain direction. All right, let's take a look at the four types of conservation of momentum. We're going to use this equation in every one. There's a slight variation for two of them, and there's some differences between them. So the first type we're going to look at is recoil. Recoil is whenever anything the two objects start together, end apart. We can do more than two objects, but we're going to just stick to two for this class. So how do they start, how do they end is really going to be the determining factor between all of our types here. So if they start together, end apart, that is called a recoil. Because they started together, they have a common initial velocity. So what I'm going to do is I'm going to say, well, V1 and V2 are the same thing. I'm just going to call it V, and then I'm going to combine them together as a single mass moving with a single velocity. And again, there are arrows on these. They are vectors, don't forget that. Whenever this happens, we have energy gained. Okay, so let's go ahead, we'll walk to the back, we'll take a look at an example of when I got two objects starting together, ending apart, and we gain energy. All right, so here we have our recoil example. So I have a cork and a shampoo bottle here, and what I'm going to do is I've put two little nails in the side of this shampoo bottle, and they're not touching inside, they're just slightly gapped apart. And I'm going to take some ethanol, spray that ethanol in there, and put the cork on the top. Now what I'm going to do is I'm going to shake this up. So what am I doing? I'm kind of letting that alcohol get around in there, and especially I want it to vaporize, because what I want to happen is I want the oxygen in that bottle to mix with that ethanol and get all next to each other, so that when I put a spark in here, we're going to get a little bit of combustion. And when we do that combustion, we are going to see that air in there heat up and expand, and it's going to push the cork one way and the bottle the other way. And so we should see that when we do this, since the objects have different masses, the larger mass, the bottle, should move this direction at a slower velocity than the cork, which has a smaller mass, moves in the opposite direction. They'll have different velocities because they have different masses, but they should have the same momentum. So how we're going to do this is we're going to go ahead and use our Tesla coil here. This creates a nice little shock, and so we're going to go ahead and shock that. All right, the slow motion camera's on. Let's go. They fired all right, and we noticed that the cork went that way at an extremely fast rate, where the bottle went the other direction at a slower rate. All right, so that was an exciting example. So on to our next one. So this is an example where they start apart, end apart, and there's actually two types that actually start apart, end apart. So they're both using the same equation, whether it's inelastic or elastic. Two things going in, hitting each other, and bouncing off. So they have initials and they have finals. They're all separate. But our difference lies here when I start to think about, was energy lost or gained? So in an inelastic collision, in a collision which you would maybe usually expect, like when two cars collide, they hit and they maybe bounce off one another, kinetic energy is lost. And when I say kinetic energy is lost, that means it's lost to things like heat, sound, deformation. And so we're losing energy there. Elastic collisions, on the other hand, conserve energy. And so this is really hard to, and rare, that two objects will interact and no sound will be produced. And so in this type of situation, we have to have two things have a force that's a field force between them. So the first thing we're going to do is we're going to look at this inelastic collision. So I have an example. It's a YouTube video, so you're going to have to go down into the description or back to the link on the Canvas page there to watch that video, and take a second, just scroll down to the description, click that link for the car crash video. All right, so we saw those two cars collide in the explosion of plastics and metals, as they say. So in that collision, there was a lot of energy loss. There was a lot of deformation. There was a lot of sound. And so we know that was an inelastic collision. All right, I had one other demo for inelastic collisions. So they start apart, end apart. And the example I have has two different balls. One of them bounces, one of them doesn't. And I want to see what happens when I roll the non-bouncing ball down, it strikes this block, versus the bouncing ball, and why that is occurring that way. So I drop the non-bouncing one down. It doesn't knock the board over. It does bounce a little bit, and the bouncy one, however, when I roll it down, does knock over that block. Why is that? And the reasoning is that that bouncing one, because it bounces, there's a larger change in momentum for it, and that larger change in momentum for the bouncing ball gives a larger change in momentum for the block. And so that larger change in momentum thus knocks that block over. So what would be an example when two things would collide or interact with a force but conserve energy? And I have two examples for you. The first one, if you remember back to chemistry, there was the Rutherford gold foil experiment where that alpha particle came in and most of them went right through that gold foil because matter is mostly made of empty space. But a few of them rebounded back, meaning they came in and they interacted, they collided with that gold nucleus. And when those two particles, the atom's nucleus for the gold and that alpha particle, both positive charges because they're made of protons and neutrons, come close, those positive charges repel, and the closer they get, the stronger that repulsive force. And so those actually never touched. They got close, and then it bounced off without actually touching it. It was just repelled by that electrostatic force. And so without actually touching, that would be an example of an elastic collision. The other example is when two objects interact gravitationally. This would be an example when we send a probe or some sort of spacecraft through the solar system. We tend to use a slingshot technique where we bring the spacecraft in close to the planet and then send it past it, and it gravitationally gains momentum because it siphons some of that momentum off of that planet. Okay, so that would be another example where they didn't actually touch, there wasn't actually sound or energy transferred. Well, there was energy transferred, but the energy was conserved. Okay. How we can test to see, did it lose it, did it conserve it, did it gain it, how much? We can use the change in kinetic energy equation I got down here in purple. So we have here the final amount of kinetic energy. So I add up the final kinetic energies of the two and subtract off the initial kinetic energies for the two. So we can use that kinetic energy to figure out if it was lost or gained or conserved. Our last example, we're going to start apart end together. So perfectly inelastic collisions. Perfectly inelastic collisions is when they stick. And so this might be an example where I throw a piece of clay at the wall. Again, when that clay sticks to that object, whether it's the wall or maybe I just throw it at an object, it's going to stick. And so afterwards, they're going to have a common final velocity. So the initial velocity and the final velocity for one and the final velocity for two are the same. Energy is typically lost. Think about that clay hitting that object. It's going to deform and there's going to be some sound.